I'm gonna take a picture of y'all showing up here on a Saturday morning, because if it didn't get Instagram, it didn't happen, right? Actually, I don't even have an Instagram account, so that's how old school I am. And today, Robert and I are gonna talk about how open data science opens the world of innovation. And there's a lot of opening there, a lot of banging too. Really, to start with, I think it's good to sort of back up a little bit and look at a high level. We're here at a PyData conference, the 23rd PyData conference, major PyData conference in the last 4 years. So it's actually really, really cool. And we're here to talk, obviously, about data science and big data and all this stuff. But I think it's good to at least have the articulation and to think about this framing that right now the world is really on the cusp of a data revolution. Even though Hadoop is 10 years old and we've been talking about big data for what seems like an eternity now, we really are just at the beginning of what I would call the data revolution. Just like I think in the 90s we went through the internet and kind of the telecommunications revolution, right now we're at the very beginning of a data revolution. And it's no surprise to any of you, probably, that data is everywhere and it's going to be even more and more dense everywhere. And this poses a problem, of course, for lots of people. It poses opportunities too. But one of the things that I think it's good to look at and ask ourselves is, well, what's the problem? Data's everywhere. We can make lots of computers, right? And also, we can just make computers faster, right? That's actually a question I get sometimes. Why don't we just make computers faster? And because a lot of the challenges we face really is because computers are slow relative to the size of the data and relative to the things we want to do with that data. And this little chart, really lovely little chart, shows the generations of processors and processing capability, and it shows how things really leveled off in terms of frequency, in terms of the amount of power you could really pump into a chip, and all that really started tapering off towards the end of the 2000s, and in around 2010, it was clear that we're all going to be living in a parallel computing world, a distributed computing world. We're not just going to be able just to make a single big fat chip anymore. And the challenge there, the reason why that's structurally different than simply writing your code and running on a faster chip. Well, I could just take the code and run on many chips, right? Now, for people in this room, how many of you have tried to do any kind of parallel or distributed computing? Show of hands. There you go. How many feel like you really succeeded and done it well? Awesome. I'm going to call you guys down here at the end of the session. No, so the challenge is with distributed computing, parallel computing is hard, and it's hard for kind of a weird reason. There's a really great quote that that I love from this particular General Barrow, and he said, when it comes to military, amateurs think about tactics, but professionals think about logistics. The tactics of how someone hides in a bush somewhere to shoot someone else, or how you fly these planes in to bomb this thing, whatever. That's all for the amateurs. The professionals think about how do you keep those soldiers fed? How do you get bullets to them? How do you take the wounded soldiers out of the combat situation? All of those logistics, the trucks are actually the more important thing. The tanks have the big explosions. The trucks are the more important thing that win the war. And so in a similar vein, when it comes to programming, I like to say that amateurs think about functions, but professionals think about bandwidth. And it's really, that's the challenge, is that when you're faced with a parallel or distributed computing situation, you now have a topology of things that are connected by very different heterogeneous bandwidth, heterogeneous latency sort of interconnects. And in thinking about that, basically everything you knew about computing, if you're at the age which the kind of the median age of this room as I look around, everything you've known about computing basically is now wrong. Everything you've known about computing is actually not the most important or the hardest problem. And so the problem is not that data is everywhere. The problem that we're faced with nowadays is that everything around the data is changing. Everything around the data is changing. If it was just big data, okay, that'd be a problem, but we could sort of work that out. The problem is that all this other stuff is there. You have GPUs now that are, have massive levels of performance, and now we have people like Amazon telling us we should be thinking about not computers and servers and things like that, or even networks of computers, but we should be thinking about distributed and streaming computing topologies elastically provisioned in some magical cloud that they own. And every other vendor also has magical clouds now that you can also buy. And then you have people creating software technologies that want you to sort of on the one hand, stop thinking about the operating system. On the other hand, deal a lot with operating systems. But whatever it might be, you're not just writing code anymore. You have to be thinking about all of these different things around it. And if you think about what Hadoop did to the data warehousing market, and the way it fundamentally has changed the conversation around that, that's one manifestation of one vertical in the big, broad, complex IT space. Hadoop is only one vertical manifestation of this level of disruption. Everything else is also going to be disrupted in a similarly fundamental way as people actually have to go and revisit and deconstruct 25, 30 years of assumptions they've made. So, and the reason that's important for us here in the data science community and the data analytics space is that most of the businesses in the world are running at the core, like beating heart, or like in the deepest part of their brains, the analytics that they run, the way they think about their business at an operational level or at a strategic level, those are driven by ideas and by technologies that are very, very, very old. And even things like NumPy, which might be new to some of you, and certainly here in the broader marketplace, people are about, oh, these new data science technologies like Python and NumPy. And it's like, well, it's not that new anymore, right? And one thing I don't have on here, of course, I don't have Excel, but Excel really is also from the 70s, right? Because VisiCalc, it does not change tremendously from VisiCalc, which came around in the 70s. So the way we think about the world, the way we think about asking questions and getting answers to them from computers, that is, it's all based on old stuff, which has been built on a bedrock of computational infrastructure and computer science and systems and all those things that have been relatively stable for a long time. But all of those things are changing now. And so it's not that we're in the middle of a data revolution, it's that we're actually in the middle of the everything revolution. And so the data revolution is really just beginning, but technology innovation is accelerating because all of the things around data are changing. And every aspect of how we ingest the data, how we're going to store it, how we're going to manage it, how we're going to compute on it, all of that is changing. And so to go into a little more detail, give you a little more color around the kinds of foundational, like plate tectonic level changes that are happening in the computing landscape. Robert will go through some of the really cool things that they've been working on at Intel and just talk a little bit about each of those things and the potential. I would encourage you guys to think about how those things could fundamentally change how you're thinking about your problems, how you're thinking about your data.
Hi, okay, that works. I'm Robert Cohn from Intel, and I'm also from Boston area, and my coworkers didn't tell me I needed a joke, so I'm going to work on one real quick, but this banger reminds me that I was giving a talk last year. In the middle of the talk, everyone was cheering and clapping in the middle, even parts I didn't think were that amazing. And later I found out that World Cup soccer was going on, and everyone in my audience was live streaming soccer at the same time, so that's my joke. Okay, and so as Peter said, a lot of things are changing, and so Intel, data science, especially machine learning, it's an important area for Intel. We think that maybe 20% of the world's servers will be dedicated to machine learning. It's a big initiative for us, and we're putting a lot of effort into making it faster. And I picked out some of the technologies that we're developing that I think would have a big impact on data science and machine learning specifically, especially deep learning. And some of the things are not totally new, but are becoming more relevant, and I'll explain why. So the first is this FPGA, and FPGA is a field programmable gate array, and instead of programming it with code like Python or C code, you can actually program it by laying out the hardware, the adders and the multipliers and the registers and things like that. And so that's the software for that FPGA. And so the reason why that's interesting is that you can really make, if you have an algorithm, a well-known algorithm, well-defined algorithm, you can actually lay out the data path for that algorithm with the ads and all that, and just have just that part of your algorithm in the hardware, and not all this other stuff that we have to normally put in to make your program work. So you can customize it to the operations you need, the data widths, and so forth. And so you can make something really, really efficient with higher throughput because there's more parallelism and lower latency. And so FPGAs are not new. They've been around for about 25 years. And what's actually changed is that Intel's integrating the FPGA into the package with the CPU. So instead of FPGA being some exotic hardware where you have to build a whole board around it to use it, it'll be in the system. So there'll be acceleration for things like deep learning in the FPGA. It'll be in the CPU. And so definitely from Python, you'll be able to just get the benefit of that kind of acceleration that's really customized to the application. And analytics, I think, would be a big part of that. And so here are some of the domains where it's be useful. And okay, this order is a little different from mine. Okay, let me just go ahead one. So here are some examples where today where FPGAs are being used for a data-centric application. And this is not the integrated one, but the one that you can buy today where it's a separate chip. So these are big companies that are able to build their own hardware, but in the future it will be accessible to everyone. And so Microsoft is using FPGAs to accelerate search. And so for a 10% increase in power, they can double the performance of the throughput in search. So it's a really power-efficient way to make things faster. You could buy twice as many servers, use twice as many power, but you can also use FPGAs, and it's much more efficient. And for Audi, for Audi, they're incorporating FPGAs into the autonomous driving. And so for there, the problem is that when you're in a car, you can't plug into the wall. And so you have to be power efficient. And so FPGAs make a lot of sense there. So for autonomous driving, which is driven mostly by deep learning, it's really going to be a big change. Okay, and this is just some more detail on FPGAs and deep learning. This is an older version of my slides. Maybe I'll switch. Yeah, okay, do this quick. And the next thing I want to talk about is 3D crosspoint. So 3D crosspoint. Okay. So 3D crosspoint is a new type of memory technology. And it looks a little bit like storage and a little bit like memory. It's sort of in between. So if you have a laptop today, you have RAM inside the laptop, probably have 4 gigabytes, maybe 8 gigabytes of memory in that RAM. And when things fit in RAM, things are fast. When it doesn't fit in RAM, either it doesn't work or it's just really slow. And another part of the system, you have a hard drive on the other end. The hard drive, instead of being 4 to 8 gigabytes, can be 500 gigabytes or a terabyte or something really huge. And so which is great, but a hard drive is literally literally a million times slower than your RAM. So you can imagine when things are in the hard drive, it's hard to make things fast. Sometimes you can do it, but it makes things difficult. Then there's something called SSD, solid-state disk. So a lot of people have laptops today with solid-state disk inside, and it's a lot faster, and it has similar density to the hard drive, maybe just a few hundred gigabytes is the normal size, and it is a lot faster. Maybe 100 times faster than your hard drive, but it's still 10,000 times slower than the RAM. So when things don't fit in RAM, even with an SSD, things are going to be slow. And so with 3D crosspoint, it has similar density to an SSD. So you can have a 3D crosspoint with a few hundred gigabytes or maybe a terabyte. But instead of being 10,000 times slower like the SSD is, it's about 10 times slower than RAM, within a factor of 10. And so we're used to this 2 times improvement every 2 years that we get from hardware, but you really get a 10 or 100 times improvement, which is what you're getting with the 3D crosspoint. So you can treat it either as storage because it's persistent when you turn off the power, the bits are still there, or you can treat it as memory, and it has different aspects for different applications. This is looking at the performance of taking an SSD and replacing it with 3D crosspoint, and which we call Optane. On the left is the latency. So Peter was talking about throughput, but also latency is important for parallelism as well, and that's where a lot of the things I'm talking about today make a big difference. So the latency of an access of an SSD is about 90 microseconds, and with Optane, it comes down to about 10 microseconds. The pink stuff here is the software overhead. So you notice that the software overhead doesn't go down. We just changed the hardware, and the software is still there. So the software overhead is really limiting the benefit you get from this new 3D crosspoint memory if you treat it as a disk. So it'd be nice to get rid of that software overhead. And the software overhead's coming from the kernel and the drivers and stuff like that, which can't just be eliminated totally and still be a disk. But if you treat the 3D crosspoint as memory, I said it could go either way, it's fast enough to be memory, then you can get rid of the software overhead. And you can see that the access time goes down to almost nothing. So now you can imagine if you could have a few hundred gigabytes to up to a terabyte of memory in your system instead of 8 gigabytes or 128 gigabytes that you can have today for a big server, you can fit a lot more data in memory. You can access it 10 to 100 to 1,000 times faster than you can today if it's in disk. And that really will enable a lot of optimizations and innovations for data science. And as Peter says, it's probably people here who will be developing those algorithms or finding those applications that could really benefit. And it's really a big opportunity that rarely happens in a career. And so we've done some simple experiments. GraphLab is a graph database that can handle data that doesn't fit in memory. And so you can take GraphLab and just replace the hard disks with Optane-based SSDs, and that'll make it faster, no change to software. Or more interesting is to take the GraphLab and to just, instead of using buffers that fit in memory, conventional memory, use buffers that fit in 3D crosspoint memory, which can be like 4 times bigger. And so you can solve much bigger problems and keep things in memory. And this is early work, so I can't show you any numbers, but the results are really promising. This is some benchmarks of replacing SSDs with Optane SSDs, and for I/O-intensive benchmarks, not all Python, and you can see that things are about 4 times faster with very little, really no change in the software. In parallelism, Peter showed how things flattened out in terms of the frequency, but actually the performance continues to go up. And the reason is because this use of parallelism. And so everyone said they're using parallelism and not using it successfully, but I think maybe you don't all realize that things like NumPy and SciPy are parallel under the covers. And so if you're using SciPy, if you're using Anaconda-based distribution, then you are, and you're solving big problems, and you are using parallelism, you just don't know it. So I think that's really a great result that the Python and especially the NumPy community made happen. And so here's sort of the hardware side of that. Maybe in 2000, you had a single core processor, and then Intel doubled the number of cores, added multi-core, and today, a few months ago, we released a processor, Xeon Phi, with 72 cores in a single socket. And those are not like special purpose processors. Those are cores that can actually run Python and have a numeric pipe in them, so they can do heavy-duty work. And Python, NumPy, SciPy will take advantage of that with no change. So I think that's really a big improvement that's happening. Much more computational power in a single socket, a single box. And on the right-hand side is showing the vector instructions. And so in 2000, you could do 4 single precision instructions in a single instruction, and that's increased by a factor of 8 over the last 4 generations. Now you can do 32. And there's actually 2 vector pipes, so you can do 64. And so it all multiplies out. So there's a huge amount of computational bandwidth inside your processor today. And if you kind of multiply all that out, number of cores times the SIMD, vector instructions times multiple pipes, then you'll see that in a Xeon processor, which is a typical server processor today, you can do 700 floating point operations in a single cycle. If you have the Xeon Phi, you can do 4.6 thousand floating point operations in a single cycle. And 15 years ago, you were doing 4. So you can see it makes a big difference. OK, so FPGA I covered. And I'm just going to wrap up. How much time do I have? 2 minutes? OK, so OK. So so the Intel is working on the right-hand side of this chart, and I kind of explain what's going on. And so to enable that hardware, you need software. So we do the OS, the compilers, the libraries, and all that, the low-level software. And we've been mostly focused on making that work from C and Fortran. And so from C and Fortran, things are in good shape. But we're ignoring Python. We sort of assumed that would happen. And so companies like Continuum and other companies in the Python community did a lot of the heavy lifting. But there's sort of part that's our responsibility. So we've been more involved than last year. We've been working closely with Continuum. And we see that Anaconda is like a way to deliver that performance. And I said that if you're using SciPy today from Anaconda, you're doing parallel processing. You just don't know it. And so we're kind of really focusing on that more in the past year and making sure that all those things I talked about before are at least can be accessed directly from Python, used automatically, FPGA, multi-core, and all that. So all these things are coming. You don't actually have to do anything new to take advantage of a lot of this, but I think it's going to open up new problem spaces for you to solve that maybe you couldn't solve before. And I think that's what's really so exciting. And just to show you some of the performance results, in this chart here, this is showing linear algebra and FFT on the Xeon processor. And the little bar here is performance of, if you just took Ubuntu and you installed apd-get, the SciPy, NumPy, all that, this is performance you get. And the black is if you're a little more sophisticated, you compile the Python stuff yourself using the defaults with OpenBLAS, and higher is better. And the blue is for an Anaconda-based distribution. And you can see that it's really very close to 100%, which is native performance if you use C or Fortran. So from Python today, you can really get, for certain algorithms that fit well, you can really get native performance without having to hand code everything in C or assembly code and all that. And you can use multiple cores and the SIMD instructions that I mentioned before. And this is the same kind of results for scikit-learn with 50% to 8 times speed up. This is principal component analysis, PCA, on Spark, and there's a 10 times speed up for that. And here's one more result. This is showing the performance. We took PCA on Spark, and we implemented it with C, we implemented it with Java, we implemented it with Python. And this is performance, and you can see they're all within 5% of each other. So it really shows that you can really get great performance from Python, and you can take advantage of multiple nodes on Spark, multiple cores, the vector instructions, all there, and it's really, relatively easy compared to what it could have been. And I think that this new computational power that I talked about earlier in the talk will be accessible to you, and you really just have to think of the right problems to solve in order to take advantage of it. And I think that was it. And this is our optimized packages for Python. Thanks.
What I am hoping that you get a sense of is just simply how much amazing new things you're going to see, not only coming now from the algorithm side and the breakthroughs in deep learning and things like that, but at a raw hardware level, things are different now. We're at a different phase than we've been in for a long time, and what I'm suspecting, what I'm predicting, is that it will lead to something akin to like a Cambrian explosion in terms of the number of different ways of trying different kinds of techniques on different kinds of hardware topologies and different kinds of hardware configurations for different kinds of problems. Like everything is going to get a lot more heterogeneous, a lot more variegated than we've ever seen. at this point, and I still, in a lot of, when I talk to users and customers and potential customers, there's always these questions of, well, what is the best stack? What's the best thing to do for this? What's the best thing? And we're going to hopefully, everyone will start realizing that you can't ask that question. Like, it doesn't make sense because there is no single best thing for everything. You don't just take this one thing and use it for everything. There's going to be different approaches, different kinds of configurations for different kinds of problems. And that's going to lead to some really rapid evolution. That's what we saw sort of in the Cambrian era as well. And one of the things that I like to, one of the metaphors I like to draw upon is this idea of, companies that are operationalized on data science, companies that are moving quickly to modern open data science. They're like, those early life forms that first started developing eyes and first started taking, light-sensitive cells, turning them into photoreceptors, and then shaping them ultimately into optical circuits that actually could image and see when there was a predator or where there was prey. And you think about the massive advantages that creatures that could see that they had versus creatures that couldn't. And even if you have a crude eye and only one of them, you're still way better off than something that can't see at all. It's night and day, literally night and day difference, right? You can't even compare. And I think companies nowadays are in a similar way. If they're still, 5 years from now, sitting there with Excel spreadsheets, driving a bunch of old reporting BI software, they're just gonna be, they're gonna be like lunch for somebody. But beyond just eyes, if you think about what eventually happened, right, as creatures evolved eyes and we move forward, it was important that those eyes actually took all of that input and was able to synthesize them in a very complex neural structure that could process those things. And so it's very important, if you think about our modern, very advanced visual systems, it's not just the eyeball, not just the retina or the fovea. Actually, what makes vision amazing is the fact that we have a visual cortex that's able to learn and synthesize all these things and is able to connect that raw sensory input and turn it into understanding and then make predictions, and accurate ones, about the world. And so in a similar way, I think businesses, as they grow and evolve in this Cambrian era, as they are able to access, 3D crosspoint, as they're able to think about new algorithms in FPGAs and work with research institutions to develop new approaches for old problems on this new amazing hardware, one thing that we have to sort of think about is how does that, though, all the technology aside, how does that actually synthesize into something, how does that turn into something that, that at an organizational level, a company or even a country can actually, not just have it be an oracle, not just have it be magic, not just have it be some super uber sky mind thing that tells you what to do. What we actually need is to have a really good interaction, a symbiosis between all of this technology, all of these data sensors and data collection methods, and all of the people who can actually make the judicious calls, who can actually ask the right questions and know which questions are better than other questions. And so I predict that in addition to us entering this era of this data revolution, that we're actually entering an era of data literacy, where the ability to think statistically, the ability to think and understand about models and how flawed every model must invariably be, the ability to explore data and talk about that, that is a new kind of literacy that will be required for any field, whatever field you're in. Whether you're in government, whether you're in genomics, whether you're an astrophysicist, it doesn't really matter. You are going to be swimming in data. And the only way to not drown, well, you're going to be covered in data. You're going to be awash in data. That's the right metaphor. You're awash in data. The only way to not drown is to learn how to swim. And that is this data literacy concept. And just like now most people can type and everything, it's just sort of a computer skills, typing skills, that's just part of the game. So I think in the coming era, we're going to see that the ability to think statistically, the ability to know what's possible computationally, that's a part of your literacy as a high-functioning professional in any field. And one of the things about that, though, the reason I use the word literacy, and it's a very intentional choice, the reason I use the word literacy is because language ultimately is a human instinct, and it's a natural, I think for us, for the way our brains are wired, it's a natural path to insight. And when I talk to people who use Python, and whether it was early on in my career, and everyone was just talking about the zen of Python and how it just sort of works, and it's like executable pseudocode, and all of the wonderful things people say about Python, ultimately it was an expression around this concept that there's actually low impedance mismatch between how we think about things and how we're able to then code our ideas. And so that expressiveness and agility, I think, is a key feature of Python, and it's one of the best and beautiful things. And one of the challenging things, however, is that it's a really hard thing to just defend. You don't have just like a CI process running for every commit that says, was this code expressive? Was it beautiful? No, sorry, you can't commit that. You can't merge that commit. You know, if we had that tool, it'd be great. But it is such a, it's sort of a wishy-washy, sort of like a very, very fuzzy thing to defend, but it is a principle nonetheless that, that we've always defended in the Python world, and I think we'll continue, hopefully, you know, carrying that torch forward. And so, you know, the punchline of that is that if you actually are able to give human brains the ability to seize upon their language instinct, you're able to give them something that is computational in addition to that. So you can take that language instinct and connect it to computers. Then what you have is not just software. It's not just a VM and a runtime and the GIL and all this other stuff. It's actually thoughtware. It extends the reach of the mind in the same way that mathematics extends the reach of the mind. We now have to do math on certain kinds of hardware, certain kinds of computational systems. And the way to do that math, the way to think and reason within that kind of scope is to use a language, and a language that lets you both think as well as compute. And a slide that a graphic that I really, really love is for people who don't know much about Python. For hopefully many people in this room, I see a few nodding heads, this is sort of like, oh yeah, of course, this is my lived experience. But for many people who come and ask me, well, what's the difference between Python and Bash? You know, I have to show this slide. And the difference, right, is that most of us who can see the spectrum of different kinds of people. There's programmers who know how to write code, who understand software architecture. And then there's analysts who understand domain problems, who understand the texture of the business problem they're trying to solve. But they really can't code at all. And they tend to be more Excel users, BI tools, you know, visual tool users. Over here, programmers, they have an editor, and that's really, they're fine with that, actually. And in the middle, we have this emerging class of people. Most of you in this room, I think, probably fit in the middle. And you are not writing code just for code's sake, nor are you just sitting there clicking around hoping that the tool someone built 30 years ago will give you the answers you need. We laugh, but we should be crying, right? It's true. And so in the middle, you are going to produce code that produces insight. And that's an amazing thing. And the even more amazing thing is that you don't have to learn some new weird thing. You can actually use Python, and it spans both. If you make a Jupyter notebook, if you make a small Python script that does an Excel query, pulls some stuff, you know, changes some of the fields around, and then sums it and computes a mean or something, you can take that script to an Excel user, and they've never taken CS 101. They don't know a malloc from a free from a hole in the ground, but they can probably edit that script and change it to query for 2 weeks ago as opposed to last week. The ability to riff off of your code is an amazing thing, and that lets that Python be very viral as a technology within firms. At the same point, you can take Python code and give it to your backend Java or Ruby programmer at your organization, and they might not know the details of everything about the syntax, but it basically can make sense to them. It makes a lot more sense than if it's SAS or MATLAB code. And they know how to deploy it. They can sort of Google around and look in Stack Overflow and figure stuff out. And the fact that you can use one language not only to express your ideas, your mathematical, statistical, computational ideas, your domain ideas, you can express that to the computer, but you can also express it to other people. And so it really can be a unifying bridge. And the reason that's so important is because based on everything I've seen, in real life, real world situations, data science is always a team sport. Data science always is not its little silo, its little ivory tower, just schlepping insights off to the rest of the business or the rest of the organization. Data science is a team sport. There's people of varying degrees of skill, even within the data science, just the data science practice. But data science is always interacting with and contextualized in the middle of a bunch of business questions, business operations, as well as a whole bunch of IT and software and IT infrastructure. And so it's important for us as we move forward into this Cambrian era of all these technologies and everything, it's important for us to consider what that heterogeneity means, what that disruption means. A lot of these people are going to be used to tools, and they're not used to those tools changing. A lot of people over here don't care about tools, and they're going to have to start caring about tools. And so data scientists actually, by being sort of a hyperspectral group, you actually can be a glue. You know, Python is a glue language. Data science actually can be a glue community, bringing all these people together into this new world of computing. And that community concept is incredibly powerful. And this slide, it's a simple slide, only 5 numbers on it, but it's actually a really amazing slide if we think about the fact that just how many we started Continuum 4.5 years ago. Anaconda is about 4 years old at this point. And the number of downloads are just skyrocketing. I mean, more and more people, most of you probably don't download a new Anaconda release, probably just Conda update, right? But more and more people are downloading Anaconda every day. Like the second derivative is positive. And I can say that to this group. And so what that means viscerally is that my bandwidth bill is actually starting to become pretty daunting. But actually, it means that we're going to have more and more people entering the data science community that are new to Python, maybe new to computing in general, and they're at universities and colleges. They may be longtime professionals who've been doing data analysis for a long time, and they're like, okay, I got to get into this data science thing. And they get a book and they get Anaconda and they start learning how to do some basic things. And so the user community is growing, and it's folks like yourselves that are going to come out to a PyData conference on a Saturday. It's folks like Capital One that sponsor these things that are key drivers in this. They're going to make this actually be a powerful movement. And it's really amazing to look back. This is not even all the talks. This is just a small smattering of them. I don't believe there's any duplicates. But we've had 4 years, we're 23 conferences now, this is 23rd, and hundreds and hundreds of talks from people. The community around PyData is absolutely amazing. And the talks, I'm not able to go to all the events, and even when I do, I'm not able to go to all the talks. But as I watch the videos afterwards, as I look at even the proposals that come in, ones that we unfortunately can't accept because we don't have enough time, all of them are just, it's so amazing to see the power here. And that power is the idea that we have a community, I think, is a central one here in the Python data science space. But the key aspect of it, what makes it click for people, I think, is this idea of empowerment. That people actually, when they're equipped with these tools, with these open data science tools, when people are able to get the data they need and they're able to go and run whatever computation they need, there's a deep sense of empowerment. And it's actually something that as we move forward and we have a world that's more connected, a world that has more and more sensors, more data available, as more policy questions shape the nature of our world, as more of those policy questions are answered by data, drop-on data, we're going to find that this data literacy concept, this could be one of those times when we either create a two-class society, where we have people who understand how all the technology works, people who understand how the data analytics comes around, that drives the policy, or we have, only people don't, or we have a world where it's very democratic, and everyone can have access to it. And so one of the deep goals, the reason why we made Anaconda, the reason why we believe in open data science, is that our world is going to be shaped by decisions, by statistical models, by algorithms that some of you here may be pioneering. And that world, in a just world, in a good world, that world and all those kinds of mechanisms should be transparent and accessible to everyone. They should not require some expensive proprietary license for someone to understand why their tax bill is this, or why they're denied this insurance claim, because they were part of some cohort that some intern messed up, right? They should be able to look at those models. That transparency and that accessibility ultimately is about empowerment, and it's ultimately fundamental to the nature of democracy and to the world that I think we want to live in. But this also, it poses business challenges. There's a long hill to climb, a long slog, a lot of fights to be had. But ultimately, I think we're on the right side of history in actually, every time in history, if you look back over the thousands of years of human history, every time that literacy or some concept like literacy has been brought into the masses, it's created so much prosperity. It's created so much wealth, relieved so much suffering. And in all those situations, there's just no argument which side of history you should be on. I think right now in the mid-2010s, we are at that kind of moment in history. And we're right here sitting on top of some technologies, whether it's hardware, whether it's software. We're sitting here and we could be champions of technologies that are open, that are democratic, that are accessible and empowering. And so I think those fights are worth fighting, and I think that we're just getting started. PyData, the concept itself, is only 4.5 years old. The community is actually much older than that, but they've all rallied around this banner that's only 4.5 years old. And the diversity of experience that we get from newcomers is absolutely one of our core strengths. And that's something that I want to reiterate to all of you, whether you're new or whether you've been here for a long time. There's going to be, if we're successful, the very definition of success, the visceral feeling of success, is that you're always surrounded by people who don't know what they're doing, because they're new. because that means you are gaining mass and gaining community and gaining momentum. If you're only ever surrounded by the same people you've always known, then you're in a dying technology space. You're in a community that has atrophied or plateaued at best. So the visceral experience of PyData, the visceral experience for you as Pythonistas in this community is that you are going to be interacting with new people all the time. And I would encourage you, and I would just reiterate that openness and the welcoming nature of Python itself as a value, but also to the PyData community, that open and engaging nature is core to what's going to make us successful as a technology and ultimately as a movement, as a community. So open data science, not only languages, not only hardware, but actually it's about empowering people to answer the questions about the world that they have. It's about inviting everyone into the tent. It's a big tent. And I've been talking about Python a lot, but of course in Anaconda we have R and we have support for Spark, many different things. And so it's not only language centric, but the Python community is certainly one of the few technology communities I've seen that really treat that openness and the welcoming and inclusiveness, treat those values as being a core value. And so we in the PyData community also have an obligation to continue extending that. And that's really, if we just do that, I think we're going to be very, very successful. I think we're going to have an amazing impact on the world. Thanks to all of you here, the speakers, sponsors, and organizational business partners. We're going to help bring about this age of the age of data, but do it in a way that is open and that is accessible to everyone. Thank you very much.